Hello and welcome to Conversations on AFM. I'm Dr. Elizabeth Kugler, a science communicator and your host of today's conversation, Automation of SPM with AI. To talk with us about AI in physical sciences is our guest, Professor Sergei Kalinin. He's a professor at the University of Tennessee, chief scientist of AI for physical sciences at the Pacific Northwest National Laboratory, and he has previously worked with Amazon as well as at the Oak Ridge National Laboratory. We all have AI on our mind, especially in the last few years. It has grown exponentially to the point that many of us use it on a very daily basis. This is made possible by algorithms such as large language models like ChatGPT to write emails, or for example, AI-based image filters on social media platforms. But today we are talking about AI from the perspective of microscopy to automate experiments, understand data properties, and how we can get the most out of data that we have already acquired. But before we take a deep dive into this, I'd love to hear from our guest, Professor Sergei Kalinin, about how you first became involved in microscopy and how you use it in the context of electromechanical measurements.
Fantastic question. So I guess the first time I got involved in the scanning probe microscopy when I was a visiting undergraduate student in post-tech in South Korea in mid-90s. At that time, I got an opportunity to learn what is atomic force microscopy, and in the mid-90s, very few groups worked on it, so it sounded suitably mysterious. So I decided to travel to South Korea for half a year to learn everything I could about AFM. So it turned out that I moved there. The lab was not really set up for doing that, but there was a library, and I guess I can say that at that time I read everything that was published in the field of AFM and STM from the moment they were invented till mid-90s. With that in hand, when I was looking for position as a graduate student in the US, I came to work in Don Bonnell group at the University of Pennsylvania, who was specializing on STM and AFM. And that's when I started to do AFM for my PhD thesis. So with that in hand, I went to Oak Ridge, as you can guess, to do AFM and STM, and that has become my career. For electromechanics, the story started when I was at UPenn, when my advisor said, hey, there is this interesting technique called piezo response microscopy. Would you mind look into that and see what can we learn with this way? What are the ferroelectrics are for, and so on and so forth. That's basically how it started.
Sounds like you have traveled a lot and worked in many, many different labs, which makes it super exciting, I guess. So as a scientist, my next question is very simple. Namely, what materials do you focus on, and why are you particularly interested in studying those materials?
My primary focus is more microscopy than specific materials. But as you can imagine, microscopy and materials often go hand in hand. And for material systems, I'm interested in those that have electromechanical responses. So ferroelectrics are the first class of materials. So they have relatively small electromechanical responses of order of several of picometers per volt or several tens of picometers per volt. And the great thing is that with the scanning probe microscope, we can do two things. So thing number one is that we can not only image these materials and get a beautiful pictures of ferroelectric domains, but we also can run physical experiments by switching polarization up and down. And interestingly, going forward 20 years, this capability of scanning probe microscope, not only to image, but also switch polarization, allowed us to build the first AI-enabled automated scientist. The second characteristic of the piezo response microscopy is that the signal formation mechanism, and it is intrinsically quantitative. So with the most of the scanning probe microscopy modalities, we know that they get beautiful images, but it's very difficult to take these images and convert them in the numbers or characterizing specific materials performance. So this happens for the fundamental physical reason that the signal in SPM depends on the contact area, and generally we don't know the contact area very well. We cannot even reliably calibrate it. In piezo response microscopy, the signal is independent on contact area, and therefore, at least in principle, the signal is quantitative. We can really explore material properties in the nanometer volumes. And most of the developments that I have done over the last 20 years, including the multimodal SPM techniques, machine learning enabled SPM, and so forth, are deeply rooted in the fact that our measurements can be quantitative. So I guess the third aspect is going beyond ferroelectric materials, and this is something that I've done when I and my colleagues were in Oak Ridge, was that we figure out that ferroelectrics are not the only materials that have strong electromechanical responses. In fact, ionic materials, so those that are used in batteries and fuel cells, also have strong electromechanical responses, and effectively we can use PFM to study them as well. So obviously in this case we cannot call it PFM because what we measure has nothing to do with the piezoelectricity. We call electrochemical strain microscopy, but the principle is the same. And then it goes to the point that between the ferroelectrics and ionically conductive solids, we probably cover a very big fraction of the hot topics in the modern material science and condensed matter physics. So everything from batteries, fuel cells, memories, memristors, and so on and so forth. So the right area to be in.
Absolutely. And it sounds also because, especially in the last few years, these topics are so important, especially solar cells, batteries, etc. It's such a growing field that there will be always this demand for new research and getting new insights. And also, as a biomedical image analyst myself, I love that you say that basically the data are intrinsically quantitative, which is probably an absolute dream if you think about multimodal imaging and correlating data across different measurements, really. And now that we kind of know a little bit about why you have started in this field and what the materials are that you're looking into, we would love to move on and talk with you about automated experimentation. Because when we work with microscopy and image data, we know that there's several steps where AI can be really useful, but you're really pioneering AI in a very novel way, which is also automated experimentation. And so most of our listeners might not have heard this kind of term, automated experimentation. Can you maybe explain what that means and why it is important to scientists?
So this is, again, an excellent question. And there are multiple ways how we can look at automation. So from some perspective, we can say that imagine that we have a large sample, for example, a wafer. AFM scanner range is limited. So how about we use an AFM to simply take a dense mesh of the images, so we map the whole surface of this wafer. You can argue that this is a simple form of automated experiment as well, but if you think about it, something seems to be limiting in this type of definition. So over time means that my group started to work on automated microscopy more than 6 years ago. We came to realize that what we need to think about is the operations and decisions made by human operator. So what I mean by that is that think about the day of the microscopist. You take your sample, you put it in the microscope, and then you go through the set of operations starting from tuning the instrument, finding the interesting region, potentially zooming in, zooming out, taking spectroscopic measurements of some time. But generally, all the time that the microscopist is running an experiment, there is this dialogue and decision making by the human operator. Human looks at the screen, visualizes comprehends the data that streams from the instrument. Based on this data and prior knowledge, human thinks what should be the next action to take and implements these actions in the microscope. So from this perspective, the automated experiment means that the machine learning algorithm, or if you will, AI, takes over some of the decision making done by a human. So rather than human making the decision, all the decisions, it should be the AI agent that has access to the information streaming from the instrument and making these decisions and implementing these decisions. we can expect that at least initially the quality of the decisions made by the machine learning agent would be not as good as the human operator. Again, at least in the beginning. Who knows what is going to happen down the line. But at the same time, AI agent can make decisions much faster than the human, and AI agent can make decisions for much longer than the human. So in our definition, the automated experimentation is the scenario when the decision making is augmented by AI agent or taken over by the AI agent.
That is so insightful. I'm just taking notes and I'm just fascinated to listen to you talking about this. Because as you say, there's so much decision making when you're on the microscope, and a lot of it is probably very intrinsic and you just kind of do it by kind of training and habit. So you spoke, for example, about the fact that the AI agent can actually do longer imaging and also making faster decisions. So I was wondering, do you also think that the AI agent is especially good if, for example, there is a less trained user, or to actually standardize image acquisition on the microscope?
So I believe that in the near future, we can have AI agents that will operate the instruments on the level of the beginning or average train operator. So they can be used to train the beginning operators on the long-term dream, pressing the button, and then the microscope start to work. They can start to give their performance on the level of the mid-level operator. I'm not sure that the AI agents in the near future can achieve the level of the qualified human operators. So humans tend to be exceptionally good in what they're doing, and at least over the last 20 years, the performance of all machine learning models plateaued on the level slightly above human. There are exceptions, of course. For example, the algorithms for playing chess or Go can play on the superhuman level. But that happens simply because the rules of the chess and Go are very well known. When it comes to the responding to the unknown, so new environments, new samples, new type of problems, if you will, AI is generally not that good for the time being. That's the reason why autonomous cars are still not a fact of life. They're somewhat in the future. However, operating in the fields where we have a well-defined set of rules, that's where AI tends to work remarkably well. Operating in the fields where the mature workflows are available, and therefore there are large volumes of training data are available, that's another environment where AI does remarkably well. When it comes to boldly go into the unknown and do the new things, so what is the core of the scientific research, maybe not so much at this point.
I love this because you basically say that, for example, chess has really specific rules, and this is where AI is really good and absolutely excels and on maybe even outperforming a human. But you also talk about the fact that, for example, microscopy is really complex, and so it's much more general kind of knowledge that someone needs. And AI, at the moment at least, does not take our jobs on the microscopes, which is great, which is good to know. And I guess it's also because there's so many different types of microscopes and samples and setups that to kind of being able to really feed all of this into an AI, we need much more data, and probably also much more kind of standardized data and prepared data, which also brings me to a question of like, how do you even start with actually getting a model trained? So, for example, how would you say to someone, if they're listening to this, how could they start to address this question of automating experiments, for example, in their lab?
So I think that these are actually two questions. So the first question is the question about the data. And I'm absolutely not convinced that the approach based solely on the available data is the right way forward. The reason I am saying that is twofold. First of all, the way humans learn is based on a very small amount of data. If you compare the number of games that the human chess master plays in order to during the lifetime, and the number of the games that the alpha chess or Go games that AlphaGo played before they get to the human level, the difference would be by many, many orders of magnitude. Same thing is that when the humans learn to drive the car, we use a very, very small amount of the training data before we can actually do it reasonably well. Same thing applies to running the microscope. So human brain somehow is very rapid in adapting to the new scenarios and can learn with much smaller amount of the training data or experience that ML agents. So each time when I hear that someone proposes to use some forms of the very data-intensive machine learning, starting from scratch to run the microscopes, I have certain doubts whether it is possible or not, because usually microscopy or science is not associated with the big data in the classical definition. So a second key aspect of that is that there are scenarios where big data is the right approach. So everything related to the medical imaging, anything related to sufficiently well-established workflows, for example, in the semiconductor industry, are the cases where the big data is important. Everything that's related to the exploratory research is a little bit of a challenge now, because somehow humans can operate in the fundamentally new environments, and for the time being, machine learning not really. So the field is developing very, very fast, of course. So we know that the generally trained models, for example, SAM by Meta, can be used as is, kind of out of the box. We have some experience deploying SAM as a part of imaging workflows on automated electron microscopy. But these models solves very limited set of tasks. So, for example, image segmentation. So they can assist human operator, but they are not making decisions that human operator normally do. So big data is necessary, but not sufficient.
And you already briefly touched on the main hurdles that you think are important in lab experiments, and also bring in automated experimentation to the labs. But maybe in a few words, you can summarize, what do you think the major challenges will be to actually bring automated experimentation to the labs in the future?
So when we started to work on this project, this type of projects at Oak Ridge 10, 15 years ago, both on scanning probe microscopes and electron microscopes, the biggest hurdle was the engineering controls. So we have the machine learning agent. So this can be the Python code, it can be MATLAB code, but ultimately we need this AI agent to run the commands directly on the instrument. So by now, many companies provide the APIs or advanced programming interfaces that allow us to essentially control the instrument through the Python environment. 10 years ago, that was a problem. And for example, in our first automated experiments on the electron microscope, the difficulty was that the instrument costs about $5 million. It comes with the service contract. However, if we connect it to the homemade controller, who knows what happens to the service contract. With the scanning probe microscopes, it was slightly easier simply because the base cost and therefore the price of error on the AFM was lower. And at that time, that was the biggest limitation. So by now, a lot of commercial manufacturers either provide the APIs or plan to provide the APIs, and then in the meanwhile can work with the customers to provide some of these functions more or less directly. And so this is moving up. The second part of the necessary toolbox is the machine learning algorithms. Again, 15 years ago, machine learning algorithms were available in relatively small amounts, and it's difficult to believe it, but 20 years ago, we couldn't even run simple principal component analysis on the realistic data sets. So the AFM at that time was generating much more data than the desktops of the time could analyze. So the amount of the data that AFMs generate did not change that much. This is ultimately limited by the physics of the imaging, but our data analysis capabilities have increased. That's also not a problem. Also, in terms of the toolbox, so what type of algorithm we have access to, by now we can find anything on the GitHub, and in many cases this would be something that has been well tested and explored. So the difficult part, and something that people generally, at least in my experience, don't think about until they solve the instrument control problem, is the workflow design. So when the human runs the instrument, humans makes a large number of decisions sequentially. So this sequence of decisions is a workflow. There are different ways we can talk about it. So we can represent it as the sequence of operation towards a certain goal. We can cast it as a search problem. So in some sense, we search in the space of the possible operations. We can represent it as the interaction with the dynamically changing environment. So we see the new things appearing on the screen. But in the end, it all goes to the same point, is that somehow we need to reflect the human decision making given the streaming data by the AI agent. So we call it workflow design. And this is the part that most of the time people who try to pick AI experiment don't think about. The easy way to think about this problem is to say, okay, let's assume that now you have the instrument, you have an API, the instrument is going to do whatever you tell it to do. So what do you want it to do? And it turns out that answering this question is very, very difficult, because given the same sample and the same instrument, different operators will run completely different experimental workflows.
It's so fascinating to see that even if people have the same experimental questions, they might set up the workflows completely different depending on their human knowledge, their domain expertise, but also their experience in general. So for example, if someone has always worked with one specific samples, they might approach it differently to someone who has imaged various different samples. So I love how you always bring back that you need this human expertise as well as experience when you design these workflows. So you do need a priori knowledge to actually design them, which also kind of brings me to the next question, which is more like future facing maybe. But you mentioned that 20 years ago, technology was not at the state as it is now. And right now it's obviously developing super fast. But maybe you can explain to us where you see the future of real-time decision-making and data analysis, and maybe also which role quantum computing plays in this.
Great question. And let me start with the following thing. So you're absolutely correct that the human decision-making is informed by the prior knowledge, and it is also informed by the data that is generated during the experiment. So very often human decision making is also associated with the hypothesis making, right? So even if we are choosing the career path, you make a hypothesis: if I go to this university, that would be better for my career goals or personal goals than if I go to that university. But there is also one more key element which basically sets the direction to the whole thing. This is the concept of reward. So essentially, a reward can be anything. So we can say that reward can be being well established. Reward can be discover new physics. Reward can be learning structure property relationship in the specific material. However, from the point of view of the AI, we need to differentiate the rewards and objectives. Objective is something that drives us for the future goal. Reward becomes something that can be discovered in the specific experiment. So for example, if we run the experiment, we want to tune the microscope until our resolution is such and such, then the resolution is the reward. Or we can run the instrument to learn the structure property relationship in the form of the machine learning model that can predict the IV curves given the local microstructure. So one of the key points, which is, in my opinion, is absolutely crucial for automated and autonomous experimentation, is that we can use AI if and only if the reward function is created. If the reward function is known, then relatively simple optimization algorithms can be deployed over the microscope to try to accomplish it by performing the allowable operation. So as a simple example, if I run the microscope during the first time of the day, my reward function is imaging optimization. Then my reward becomes curiosity. So I want to quantify what are the objects in the system. After that, my reward will become hypothesis testing. So I have some idea about what type of behaviors should manifest in this material. I run my experiment in such a way as to prove or disprove this hypothesis. However, humans are very good in going between the rewards and objective forward and backward. AI agents cannot do that, or simple AI agents that can run the microscope cannot do that. They need to have the rewards formulated by human. So if the reward function is known, then we can use AI, and that will have nothing to do with the large language models. It would be simple optimization workflows. So how does the reasoning system or LLMs or ML agents come into the play? So it seems that they can be reasonably good in helping human to formulate what the reward functions are in pursuance of certain objectives. So this is the case where bottom-up approach, the optimization workflows running the instrument, and the top-down approach, the large language models that can help us define reward functions, come hand in hand. That being said, the long-term objectives are still up to human, because in some sense, figuring out what is that you want to do, it sort of stops being scientific questions, becomes a little bit more question along the line of the freedom of will, which goes a little bit outside of the AI.
That was so in-depth. It was wonderful to listen to you, especially also about reward functions. And I wish we had a whole other podcast just talking about optimization and reward functions and all of this good stuff. But unfortunately, we don't have the time for that. So I kind of want to wrap up with saying thank you so much for joining us today. It was absolutely amazing to hear about your work, about your insights and experience. And it's been really insightful to hear not just about your work, but also that you see that we always need the human still in the loop. We need to have machines and algorithm development complementary to human. And so I thank you so much for your time today. It was an absolute pleasure to having you on the show today.
My pleasure. Thank you for inviting me.
That's all that we have time for in today's conversation. To our listeners, if you have not done so already, be sure to listen to episode 3, where we talk to Professor Kusheviruk, who is the director of the Lübeck Institute of Physiology, where she explains to us how AFM can be used to measure cell stiffness and its implications for cardiovascular disease and hypertension. Thank you and goodbye.
This podcast was sponsored by Bruker Bio-AFM, part of Bruker Nanosurface and Metrology Division. Bruker is a manufacturer of scientific instruments for life sciences and materials research, as well as for industrial and applied analysis. If you'd like to learn more, please visit www.bruker.com/bioafm. This podcast was produced by Keep It Science.